When this shall chapter start, we would discuss explaining certain the basic terms signals concepts, and signals are processed by systems. Signals. A signal, as the term implies, is a set of information or data. Examples include a telephone or a television signal, the monthly sales figures of a corporation, and closing stock prices, e.g., in the United States, the Dow Jones averages. In all these examples, the signals are functions of the independent variable time. This is not always the case, however. When an electrical charge is distributed over a surface, for instance, the signal is the charge density, a function of space rather than time. In this book we deal almost exclusively with signals that are functions of time. The discussion, however, applies equally well to other independent variables. Systems. Signals may be processed further by systems, which may modify them or extract additional information from them. For example, an anti-aircraft missile launcher may want to know the future location of a hostile moving target, which is being tracked by radar. Since the radar signal gives the past location and velocity of the target by properly processing the radar signal, the input, one can approximately estimate the future location of the target. Thus, a system is an entity that processes a set of signals, inputs, to yield another set of signals, outputs. A system may be made up of physical components, as in electrical, mechanical, or hydraulic systems, hardware realization, or it may be an algorithm that computes an output from an input signal, software realization. 2. One size of a signal. Signal energy. The size of any entity is a quantity that indicates its strength. Generally speaking, a signal varies with time. To set a standard quantity that measures signal strength, we normally view a signal T as a voltage across a 1 ohm resistor. We define signal energy E8 of the signal T as the energy that the voltage T dissipates on the resistor. More formally, we define E8. 20 Figure 2. 1. Examples of signals. A. Signal with finite energy. B. Signal with finite power. For a real signal, as E G equals 1 underscore G2 T dt. 2. One size of a signal to 1 A T 2 1. This definition can be generalized to a complex-valued signal T as 2.2. Signal power. To be a meaningful measure of signal size, the signal energy must be finite. A necessary condition for energy to be finite is that the signal amplitude goes to zero as ITL approaches infinity, Fig. 2. LA. Otherwise the integral in EQ 2 1 will not converge. If the amplitude OFG T does not go to zero as T approaches infinity, Fig. 2 1b, the signal energy is infinite. A more meaningful measure of the signal size in such a case would be the time average of the energy, if it exists, which is the average power Pg defined, for a real signal, by Pg equals TLMUTI at 2 grams 2 T dt. T2 We can generalize this definition for a complex signal g, t, as Pg equals TLMU T1 it 2 Jg T I2 dt. T2 2.3 2.4. Observe that the signal power Pg is the time average mean of the signal amplitude square. That is the mean square value of g, t. Indeed, the square root of Pg is the familiar RMS, the root mean square value of g, t. The mean of an entity averaged over a large time interval approaching infinity exists if the entity either is periodic or has a statistical regularity. If such a condition is not satisfied, an average may not exist. For instance, a ramp signal g, t equals t increases indefinitely as tu, and neither the energy nor the power exists for this signal. Units of signal energy and power. The standard units of signal energy and power are the joule and the watt. However, in practice, it is often customary to use logarithmic scales to describe signal power. This notation saves 22 signals and signal space. The trouble of dealing with many decimal places when signal power is large or small. As a convention, a signal with average power of p watts can be said to have power of 10 log 10 p dBW or 30 plus 10 log 10 p dBm. For example, minus 30 dBm represents signal power of 10-6 W in normal decimal scale. Example 2. 1. Determine the suitable measures of the signals in Fig. 2.2. Figure 2.2. Signal 4. Example 2. 1. The signal in Fig. 2.2 approaches O as LTL plus U. Therefore, the suitable measure for this signal is its energy, e.g., given by Eg equals FO8G2 T dt equals FO1 2 dt plus 1 0 4 E minus 1 dt equals 4 plus 4 equals 8. The signal in Fig. 2.2b does not approach O as LTL plus U. However, it is periodic, and therefore its power exists. We can use EQ 2.3 to determine its power. For periodic signals, we can simplify the procedure by observing that a periodic signal repeats regularly each period, 2 seconds in this case. Therefore, averaging G2 t over an infinitely large interval is equivalent to averaging it over one period, 2 seconds in this case. Thus, Pg equals 2 to 1 minus 11 grams 2 t dt equals 2 to 1 minus 11 t2 dt equals 3 to 1. A 1 0 2 4 1. Recall that the signal power is the square of its RMS value. Therefore, the RMS value of this signal is I3.